So my talk will be try to introduce basic concept of statistics, and I'm not sure you feel like mathematics is more boring or statistics is more boring, you know. But I'll try to make it interesting. And what I will do is, first I will give a brief introduction about what statistics is and what statistician can do for you. And then I will talk about, introduce several concepts. Here, today I'm not talking about too much on real statistical methods. Instead, I will try to introduce some basic concepts about statistics. Basically, we are trying to prepare the talk or the lectures on day 3. Day 3 will be the whole day of statistics methods. But today I just introduce the basic, preparation, basic concepts. So that's why I will try to introduce random variables and the distributions that include, discrete and continuous random variables. Then I will talk briefly about summary statistics. And probably, many of you are familiar with this basic statistics. And some of you probably have no idea about what this is. So I try to not too deep, not too, low. I mean, try to be compromised in between this. And I'll talk about, data types and study endpoints. For statistical inference, I will just talk about the point estimation today. And then we'll talk about more statistical inference on day 3 on Tuesday, about this. Then finally, I will briefly give you an overview about the statistical lectures on day 3. So that's the continuation of my talk. This is the whole day's, lecture. And usually when people talk about statistics, if you go to Google, what statistical means, the definition on the Google on the website is like it's a science. Statistics is the science of data collection, analysis, and presentation, basically. So sometimes they include data collection. Usually statisticians don't do experiments. What do you mean data collection? Let's talk about survey. When people do this survey, probably not related to your immunology study, but people do a lot of epidemiological survey or something. Usually statisticians have to go to the field to collect the data by themselves. And mostly it's analysis and presentation means to present data in a good way in terms of like the plot, figures, visualization, all those things. And the report, and basically statisticians, contribute to the scientific fields by applying our knowledge to design the experiments. Sometimes the survey, as I mentioned, this related to the data collection, survey and experiments. And also the second thing is definitely is the data collection, processing, analysis. So this is the major part, and definitely I will talk about this also. And then finally, how to interpret the results. When you get the data analysis result, if you have to interpret the result appropriately, otherwise, still you can misuse the results. So that's the 3 things statistician can contribute to the scientific research. This is the slide I still got from our president of American Statistical Association, and so this is the interview that I think to Google chief economist, Hal Ryan. That's in the year of 2009. He's talking about that. Keep saying that the sexy job in the next 10 years will be statisticians. I don't know why statistical job is sexy, but and he said I'm not kidding. And that's several, about 3 or 4 years ago. And, because before this, people always think statistician, or statistical job is boring, really boring. You just deal with numbers, right? It's the boring numbers. And actually, in this year, in the Nature, there's a news. They talk about, statistical expertise has become more valuable than ever because when people deal with the high-dimensional data or mixed data, then even in the Nature, the journalists start to talk about, the importance of statistics. That's the thing. And also, the big data problem right now. And so this is in New York Times, also in February this year. When people talk about statistical big data, they think the statistics are interesting and fun. It's cool now. So I'm not, from a very boring field. I know when people do the survey in the high school kids, what they want to do, you've given them choices. They think the statistics will be lowest choice. It's a boring job. So, but now it seems like the world is changing. To right now people think the statistical job is interesting, fun, and cool, and also sexy, which is good. Hopefully you will change your job. I'm not sure in the future to statistics. And in March of this year, President Obama, announced his big data initiative. Basically, he announced like $200 million, in new in the R&D investment, to NSF, NIH, different government agencies, try to deal with the big data. What that means is right now, there are a lot of big data issues from security, biomedical research, whatever, this surveillance, in the airport, they collect a lot of images data, and they want to identify terrorists, it's not easy, there's a huge amount of data there. So how to handle this, this becomes a problem. That's why, the government start to think about to deal with this kind of big data problem. And when we talk about the big data, definitely this data related to statistics. You have to use statistical technologies or methods to deal with the big data. So that's why I think in the next 5 to 10 years, and more statisticians are needed, wanted to work on these kind of things, That's, but when we come back, see, we are talking about a very big picture about big data. When we talk about the immunology, most of you are immunology or virology, whatever, microbiology, research, you are doing those kind of research. And so what statistician can do for immunologists? In this morning I talked about, what modeling can do for immunologists. Actually, as a statistician, for many years, I collaborated with many biologists, mostly immunologists and infectious disease investigators. That's my focus, do immunology and infectious disease research. And this is the things I usually do for my collaborators. Number one, usually I help people to design more efficient experiments, try to test their hypothesis, to address their scientific questions. Design is critical, but usually experimental investigators do not recognize that this is a critical step to involve statisticians in it. So usually what I get is they try to, like last week, one of the immunologists talked to us, I'm working on a grant proposal. The deadline is this week, this week. Yeah, this week, last Friday or Thursday, just 3 days. Could you write, help with the statistics and data management? There are a lot of, that project supposed to collect the microarray data, microbiome data, flow cytometry data, ELISpot data, and for, many subjects for every day, for like every 3 months for 30 months, a lot of data, right? But I need to write something down to design the experiment, help with the statistical section in a couple of days. But usually that's too late. We have to rush to it. The proposal, grant proposal may not be that, we don't have time to make it, perfect. Definitely that's not the ideal case. Ideally we should, so, in order to make this design really more efficient and novel, we need a lot of time to work on it. So this design is very important actually. And the second thing is definitely we can do is the data analysis. There are 2 different types of data analysis. One is kind of a standard analysis. Some of you, know how to do it. Many immunologists I know do this analysis by themselves. Click some software, click some button to do a t-test or ANOVA or even regression. I know some people do this. And definitely we can do more complicated and novel analysis, for complicated data. So that's a thing, we can help. And definitely for this, publications, and also grant application, these 2 things, if you are in the academic, world, these 2 things are critical for, for your career. So we, as a statistician, we help investigators to write papers. We help them to do data analysis. Definitely, we have to help them to write papers. And for grant application, as I mentioned, make their experimental design novel and also help with the statistical section of the grant proposal. That's our job. We are working in the medical school, so we work with many experimentalists doing this almost every day. So that's that's what we do. And this slide I also mentioned, but the question is, when we talk about immune modeling, because this program is sponsored by this so-called biodefense immune modeling project. So the question, when we talk about computational mathematical models, like Jackie, just talk about the this morning and also this afternoon before me. When we talk about mathematical models, computational models, why we need statistics? That's just mathematics. You write down the models, different equations, you can do it. So why we need statistics for modeling? So this I just list. Actually, immune modeling needs statistics from the beginning to the end. Why is that? When we talk about immune modeling, we have to use the data, use the experiment to construct the model, to validate the model. Otherwise you just write down some theoretical mathematical model is useless, right? You don't know whether it's true or not. So in order to do that, you have to do experiment. You have to collect a lot of data. When you collect the data, then you need statistics. Number one, you do the data processing, some preliminary data analysis, and then you need some basic statistics. When you try to deal with the more complicated mathematical models, such as differential equations, even the partial differential equation, like you are confused in probably this afternoon, PDE, ODE, whatever. When you do complicated mathematical models, then you need to identify those models, based on your data. So that's important. How can you use your experimental data to construct a model and also try to validate that this model is right for your data. So for this one, not only at least here the parameter estimation, but also the model structure identification. That's another thing. I forgot to list the model structure identification. So how do you use your data to identify your model structure and also identify your model parameter, and also try to do model diagnostics, evaluation, which means when you get a model, and how can you evaluate your model is good or not? Somebody asked questions, when you do a model fitting, how do you know the fitting is good? How do you quantify the goodness of it? That's needs statistics. That's a statistical method. And definitely finally for model validation. So when you build a model, then you may do another experiment to try to validate your model really good or not. So then you need the statistics to do that. Okay. Once you get the model done, you build a mathematical model for biological experiments or for biological process. Then you want to use the models for what? Usually you want to use the models for predictions and simulations. Those predictions and simulation also need statistics. So because why each of these steps needs statistics? Just because each of these steps involve data, and all the data involve randomness. So I will talk about the randomness, what that means, and so that's why from the beginning to the end for the modeling project, we need statistics. So that's why we have the whole day for statistics here. Okay. Now I start try to introduce some basic statistical concept. First concept we need to introduce is random, or random variables. Okay, this is the basic thing. When we talk about any data, any numbers, then we always, as a statistician, we always talk about, this is the random variable of something. Okay, what's the definition of random variable? If this is not a real mathematical definition, but this is a more conceptual definition. A random variable actually is a real value function defined on a sample space associated with a random experiment. Okay, so this is the definition. From this sentence, so the word, you can see that a random variable is not a variable. Okay, a random variable actually is a function. Okay, it's not a it's a random variable is a real valued function. It's not a real it's not a variable. And also, it's actually based on this. It's not a random. Also, it's not a random. It's a real valued function. It's not a random function. So, actually, the name of the random variable actually is a misnomer. Actually, it's people just because of historical reason use the random variable. But this thing is really not a random variable. It's not a random. It's not a variable. It's a real valued function defined on a sample space associated with a random experiment. Just because it's associated with a random experiment. Basically, a random variable try to describe, or it's a function to describe experiment with a random outcome. What the random experiment is before you do the experiment, you don't know what outcome it is. It's, when you flip a coin, for example, before I flip it, you don't know that's head or tail, right? After it, you know that, but before it, you don't know. So that's random. So that's the that's the concept. Okay. Then in this talk, I will try to use the mathematical notation. Okay. When I use the capital letter, for example, the capital X, or just But if I use a parenthesis here, that means this x really is a function of something. You know, it's supposed I should write down something inside of the parenthesis. But when I use this notation, I'm trying to emphasize this random variable x is a function. Okay, it's a function of defined on a sample space. And when I use a small x or small letter, this means the realization of this random variable. That means it's the experiment is done. When I flip a coin, before I flip, you don't know what is tail or head. But once it's done, I tell you, oh, the first flip I got head, and second flip I still get head. The third one I got tail. So if I write down this number, this is like a head and tail is the result. When I write down the result, that's called realizations. This is the small x. Okay, this is like a real data. It's just small letters. This is just the notation, and usually people use. So now let's talk about some so-called discrete random variables. There are two big types of random variables. One type is so-called discrete random variable. Discrete, from the word discrete, is countable. Basically, for example, if I try to if I randomly select an adult in Rochester, in the city of Rochester here, so I want to know this person's HIV status, whether it's positive or negative, right? I do a blood test and try to figure out. If I randomly select this person, and I don't know whether it's positive or negative before I do the test, right? And so this is a kind of like a random variable, and also it's discrete because I only have two outcomes, either positive or negative, nothing in between, right? And so in this experiment, if I randomly select a person in Rochester, so that means the sample space is all the adults in Rochester because I'm trying to select adult in Rochester. So all adults in Rochester, probably about, if you include greater Rochester area, about 1 million people, right? It's the 1 million people in this, sample space. I can get if I randomly select one, it can be any one of 1 million people. And the results of this, random experiments, whether this person is positive or not negative, can be, if I can assume if it's negative, I can say it's 0. If positive, I can assign this random variable as 1. Basically, this small s is a person, and this random variable, that's why we call this random variable is a function. So if I know which person, after the test, I can assign this function as either 0 if this is negative, 1 if the test is positive. So that's why this is discrete, just 0, 1, two numbers. Okay, so this is the one of the the discrete random variable example. Another one is a continuous random variable. Actually, it's hard to get a real continuous random variable. As Jackie also talked about that. When you talk about continuous variable using different equations, you always use the average of something. Otherwise, you always get a count number. Whatever you do, you get the number. So it's the same thing. If we are defining a random variable as like total CD4 T cell count per ml blood from a randomly select HIV positive adult in Rochester. I know this person already HIV positive, and I, collect this, 1 ml blood from this person, and I want to know the total CD4 count. So usually, when you do this count, it should be a number, right? It's not the number of cells. It's not really continuous. But usually, when we do this count, you don't get exactly 1 ml blood. When you do the test, probably is much smaller than ml. I don't know exactly what. Then they try to collaborate or calculate back into per ml how many CD4 counts. Usually for HIV positive people, the CD4 count can be per ml can be from 0 to 1,000. For a normal person, usually it's around 1,000. But for HIV positive person, usually it's between 0 and 1,000. And so I can assume this random variable as a value between 0 and 1,000 can be any any real number. Can be 200, even 200.3 if you do the average or something. If that's the continuous variable. And so this is the one is the random. You can count just 2, and this can be any number between 0 and 1,000. So this is the two examples of discrete and also continuous random variables. I'm not sure if confused you. Any question? No? Okay. then I try to introduce some of the mathematics, and the one thing is very important for a random variable, which is the distribution. Okay, sometimes rigorously we talk about this is called cumulative distribution function of a random variable x. What this means, this distribution function actually is the fx. So this small x means it's a realization of x, and capital X is this random variable. So this is this cumulative distribution function of this random variable x. Or usually we use CDF to indicate this. So what is this? This distribution actually is a probability. Okay, distribution function is a probability. It's the probability of this x less than or equal to x. Okay, so it's this, because x is a real valued function. This function less than or equal to a number is this probability called distribution function. Okay, because this is a distribution function, or because this is the probability, we know that probability usually is between 0 and 1. So this function should be between 0 and 1. I think this is a typo. This should be x. This is not negative infinity. So what that means is y is 0 and 1. When this x actually is negative infinity, this negative infinity means on this side is the smallest number. So nothing can be smaller than negative infinity. That's why this probability should be 0, because no number can be smaller than negative infinity. So when this small x is negative infinity, then this probability is 0. Okay. When this small x is positive infinity, so no number can be bigger than positive infinity. So that's why this probability must be sure, right? All the numbers less than positive infinity. That's why this probability is 1. So that's why I give the two limits. One is if this x go to negative infinity is 0, x go to positive infinity this is 1. So basically what that means is this distribution function of a random variable is a probability. This probability must be between 0 and 1. Okay, this is the thing. Another property of this distribution function is this is monotone and non-decreasing. Okay, monotone non-decreasing means this function must be always increasing like this way. It cannot be, maybe sometimes can be flat. That's okay, but cannot be like this way. This thing, okay, cannot drop, cannot fluctuate. It must be monotone non-decreasing, and also always continuous from right. This is from a calculus concept, and always continuous from right. It means somewhere can be there's no value, but on the right hand side must be continuous. So that's this is a more mathematical concept. Probably you don't need to know too much on the rigorous of the mathematics, but here just introduce some basic concept. Okay. So then this is the distribution function. Then when we come back to talk about a discrete random variable, okay. So again, for rigorous definition of discrete random variable, I just mentioned that a random variable with a countable range. Okay, that's called discrete random variable. Countable range means you can count it 1, 2, 3, 4, whatever. So that's called random. This is called a discrete random variable. For a very simple example is that, like I just mentioned, if you flip a coin, you only have 2 possible numbers, head and tail, or whatever you call 0 or 1. It doesn't matter, right? And when you roll a die, it's you only have 6 numbers, 1, 2, 3, 4, 5, 6, right? And that's all the before you roll the die, you don't know which number it is, but once you roll, must be a number between 1 and 6, 1, 2, 3, just 6 possibilities. So all these things is countable. You can count 1, 2, 3. So this is the good example for discrete random variables. And when we talk about discrete random variable, the distribution or cumulative distribution function also is discrete. Okay, means discrete also is countable. Okay, and very important concept for the discrete random variable, which is different from continuous, is so-called a probability mass function. Okay, for a discrete random variable. So probability mass function, what that means is because each of this is countable, and for each of possible outcome, there is a probability. Okay. For example, if you flip a coin, it can be a head or can be a tail, right? Okay. It's two possibilities. Doesn't matter which it is. There's a probability associated. It's a probability for a head. It's a probability for a tail. Okay. So for this probability, okay, it's called a probability mass function for each of possible outcomes. You flip a coin. So if the coin is a fair coin, you know the probability is 0.5, right? 50% for 50% for each head and tail. If it's not a fair coin, it can be any probability. The same thing for if you roll a die, the die number can be 1, 2, 3, 4, 5, 6. Again, if the die is is a fair die, you know the probability for each of these, right? What's that? 1/6, right? If they are equally possible. So this this probability corresponding to each of these possible outcome of this random experiment, this is called a probability mass function. Okay, so this is the very basic concept. However, for continuous variable, we don't have this. For continuous, it's so continuous, you don't know. You are looking at, for example, if you are looking at the CD4 count for a HIV person, that can be any number between 0 to 1,000, right? So this is hard to get one, probability for any number. For example, I want to get 253.598, whatever this number is. If you get a probability for this probability usually is 0. This mass function is 0, because that's a continuous number. Otherwise, you add them together is not 1. But this thing you can add them together is 1, right? And this two also add together. But this one, for continuous, we don't have this concept. If you do, then basically that for any point for a continuous random variable, the mass function or probability mass is 0. So usually we don't talk about that for continuous random variable, but for discrete, each of these probability, for any given possible outcome, the probability of this is called probability mass function. If you still remember the CDF, distribution function is this x less than or equal to x, not equal, right? That's the key difference. CDF, so this probability mass function is x exactly equal to x. The CDF actually is the probability of x less than or equal to x, small x. So this is the probability. This is the CDF function. So this is the difference. One is here, and this is equal. Okay. So this is just the basic concept about this. And for not only for discrete, also continuous random variable. Actually, the CDF and also probability mass function for discrete random variable, the CDF and the probability mass function, this is the one-to-one correspondence. What that means is if for a given distribution function or cumulative distribution function, the probability mass function can be derived. Vice versa. If you give me the probability mass function, I can derive the CDF exactly. So that's the one-to-one correspondence. So, but there's a lot of mathematics to deal with when you do this one-to-one correspondence. But I'm not going to talk about the rigorous mathematics over there. So again, for this discrete random variable examples, I already give you several of them. For example, when we talk about HIV status of a person, of randomly selected person, whether it's yes or no or positive or negative, this is the distribution actually we call the Bernoulli distribution. Basically, you have two possible values. Either you flip a coin or you test a person whether it's HIV positive or negative. So this so-called binary outcome is we follow a Bernoulli distribution. This is somebody's name we used. And another discrete random variable is if instead of I grab one person, if I pick 10 people, I test all these 10 people, see whether they are negative or positive in terms of HIV. So how many of these 10 people are HIV positive? So this is random, right? You randomly select 10 people in Rochester, you don't know how many, maybe none of them, maybe 1, maybe 2, maximum is 10, right? Totally you got 10 people. So this kind of random variable actually is called a binomial distribution, which means you just test it one by one, but you put 10 people together, you want to find out how many of them. So this is a so-called binomial distribution. There's a uniform distribution on integers. This is also a discrete random variable. I just mentioned that when you roll a die, that's really a uniform distribution on integers. What that means, you only have these 6 possible integers outcome for the possible outcome, and they are equally distributed. So this is why they call it uniform distribution on integers. So this is also a typical discrete random variable. Another typical discrete random variable, so-called hypergeometric distribution. I will not talk about today. Probably we'll have time to talk about on Tuesday. We usually use this like for gene set analysis. When you do the doing bioinformatics, do the functional enrichment analysis, try to figure out gene set functions, and we usually use the so-called hypergeometric distribution. And also there's a Possum distribution I will talk about later, give you more rigorous definition about this. Basically, Possum distribution, probably some of you know that, let's try to describe a count, a random variable that have a count. For example, the number of car accidents in, let's say, 1 month in Rochester, that's the count, how many car accidents. When you do experiment in any spot, when you do any spot experiment, how many spots in one well. So that's also random, right? Before you do experiment, you don't know how many spots. So this, Possum distribution is good description, or good. It's good to describe, those number of something, a count. Okay, so that's the thing. Okay, then let's talk about a little bit more mathematics about all these different kind of discrete random variables and distributions. First one is I think it's simplest discrete random variable distributions, as I mentioned earlier, which is the Bernoulli distribution. And for the Bernoulli distribution, basically the probability mass function of x, because as I mentioned, Bernoulli distribution means it's just 2 possible outcomes. You flip a coin, either it's head or tail, or you test some of this, whether it's HIV positive or negative. The answer is only yes or no. So only these two possible outcomes. So the mathematics, from a mathematical perspective, this is the so-called probability mass function of x. Okay, so I just put down this into one function. What that means is, for any of this x, if this, let's talk about this x. If it doesn't matter is you flip a coin, is tail or head, then the probability, I can use this formula to calculate the probability. Okay. Otherwise, the probability is 0. I mean, maybe it's possible it's not head and tail, right? It's somebody flip a coin, the coin just stand there. But we think that the probability is 0. You really still don't get it. And but if it's, you can see if you use this formula to calculate, let's say x equal to 0, let's say call this is the tail, right? And let's say x equal to 1, this is the head. Okay. If you do this based on this formula, that's easy to calculate. If your coin is fair, let's say coin is fair means this probability p is 0.5. This p means, p denotes the probability of a whatever. This is randomly selected adult being HIV positive or negative, or probability of randomly you flip a coin. What is that probability? If you have a fair coin, the head and tail probability is 0.5. It's equal probability. And when you do the HIV, it may not be equal. Randomly select person from Rochester, I don't think it's the probability is 50%. It's much smaller than that. So let's do the coin. Then I can plug this. If I let p equal to 0.5, you flip a fair coin. Then what is the probability to get a tail? So you just plug get tail means x equals 0. If x equals 0, there is 0.5, p equals to 0.5. This x is 0, is 0's power, and then 1 minus 0.5 is p, and 1 minus 0, because this x equals 0. So basically here you will get a 0.5, right? Because this is the what? This is the 1, right? Anything's zero's power is 1. And this is 1 minus 0 is 0, so 1 minus 0.5 is 0.5. So finally, this is 0.5. Similarly, you can calculate this. This is also 0.5. Okay. So what that means is if you have a fair coin, you get the probability to get a tail and head is equal. You get 50%. If it's not a fair coin, you can plug in the p. If you think your coin is not fair, it's probably the probability for the tail is p equal to 0.3, for example. Then you can plug that in, to calculate what's the probability for each of these. This is not, not fair either. So this is how we do this kind of calculation, based on if you know the p and then you can just based on this probability mass function, you can calculate the probability for each possible outcomes. Similarly, like when we do this die, when we roll a die, this you can get this number from Bernoulli distribution. But I'm sorry, this is not Bernoulli distribution. This is the uniform distribution I will talk about later. Here, okay, let's talk about the binomial distribution. So binomial distribution is quite similar to this. This is the formula here. We just have change this. There's a n select x, and also we have here is p to x power 1 minus p. Here is n minus x instead of 1. Here is 1 minus x. That's the difference. Because right now what we are trying to do is if we select n people from Rochester, we want to know how many of them are HIV positive, right? And so when we do this, all the possible numbers can be 0, 1, 2, up to 10, which means n equal to 10. Okay, so this is the formula again to calculate the probability mass function. Okay, you can just plug in all this, plug in the p and also plug in the x and n. You can do this. You can get the probability for each of these x equals 0, 1, 2, up to n. Okay, so but you need to know, in order to do this, you need to know this p. So p is what? P is the probability for any person you randomly select in Rochester. What's the probability for that person to be HIV positive? Okay, this is hard to estimate. It's hard to deal with. If you know this, then you can do this. If you don't know this, then you need to design experiment or to do a survey, try to estimate what p is. Okay, and probably p should be a very small number. I think it's very, very small, 0.00 or something. But I'm not sure anybody have done this for each of the city. There's roughly, I know the number in Rochester, how many HIV people who see the doctors in our hospital or in several AIDS clinics in Rochester, but probably still don't know the exact p. This is, in this way, we really need to design experiments to estimate the p. Again, this is another example for Possum distribution, as I mentioned earlier. So Possum distribution is try to describe the number of a count, okay? Like the number of car accidents or the number of calls in a service center in 1 day or maybe in 1 minute. It doesn't matter in a time period. Also, this one's also in some time period. And also the number of spots in a well of ELISpot. We're going to do ELISpot experiments again. And how do you calculate the probability, for example, in one well, and how do you calculate the probability if I got 0 spot, I didn't know any spot, or I got 2 spots, or got 3 spots, so this is the formula actually to calculate that probability. So this is the probability mass function. Then the lambda actually is the mean or is the average number of the count per time unit, whatever the time unit is. And but for ELISpot, there's no time. It's per unit. Per unit means either the area or the well. So per unit, what's that average count? If you know the mean count, that's the parameter you need to know in order to calculate the probability for this x equal to 0 or 1 or 2 or 3 up to infinity. So this is the Possum distribution formula. So probably some of you know this. Okay. So that's all the discrete random variable. I'm not sure any questions about this discrete random variable. Is it confused or is okay for you? Is it good? Okay, so it's basically you know all these things. So let's go to some examples and definitions for continuous random variable. A little bit of more details. So a random variable is called continuous if it can assume all possible values in the possible range of the random variable. So what that means, as I mentioned earlier, for the CD4 T cell count, okay, for HIV patient, and if this number between 0 and 1,000, let's assume this should be any number between this. So that means can be any integers, even any real number, can be any 500.35, whatever. If any number is possible, then this is a continuous random variable. If you think it's just the integer, it's not continuous. Okay, and a random variable is called continuous. In mathematical terms, is if there exists a function f(x) such that this CDF, you can remember, this, we use this notation to indicate the distribution function or cumulative distribution function, CDF. If this CDF can be read into something of integration of another function, small f(x), okay, from infinity to x. If you can write this, CDF into this form for every real number x, then we call this random variable as continuous. Okay, so this is the mathematical, definition for continuous, distribution. Basically, if you can write down the CDF into an integration of something, then this is continuous. Okay, and again, this f is called, cumulative distribution function, CDF. Actually, the inside of integration, this small f is called probability density function. This is comparable to the probability mass function of a discrete random variable. But here we call probability density function, or PDF. It's not a PDF file, but we usually use PDF. Probability density function. It's corresponding to the PMF. For the discrete random variable. So this is the more mathematics. When you talk about continuous random variable, is conceptually I can use this word sentence to tell you what it means, but mathematically it's more rigorously in this way. Okay, so that's the continuous random variable. The same thing, like for continuous random variable, the CDF and the PDF, or distribution function and the probability density function, they can be one-to-one correspondence. If you give one, you can derive another one. So so that's why when we talk about this, either we just give you a PDF or just give you a CDF. We don't give you both, because if I give you one, you're supposed to know another one. Okay, so that's either way is okay. And there's many examples. You probably already know that. In the real world for the continuous random variable, and simple continuous random variable distribution is so-called uniform distribution. It's similar to that discrete, uniform distribution, like I just mentioned. The roll a die, you have equally distributed, on the integers. But for the uniform distribution is you have equal probability on an interval, continuous interval. I will talk about this, later in more details in a mathematical way. But I leave this as a question mark, give you that as a homework. And can you give me an example in the real world? What kind of random variable really follow a uniform distribution? I leave this as a homework because it's hard for me to get an exact example, exactly something follow a uniform distribution in the real world. For this discrete, easy, like if you roll a die or something, is easy. But for this, usually is an approximation actually. And probably you'll always deal with the so-called normal distribution. Many measurement errors or many things you measure actually follow a normal distribution. This is the most popular distribution. I will talk about later in more details. Like also exponential distribution and gamma distribution, Weber distribution and beta distribution. Probably also familiar with T distribution, F distribution, and chi-square distribution. So all this, the distribution try to describe a distribution of a random variable, or describe the data set, from your experiments. Okay, I will show you some of this, from graphic or mathematical perspective. So this is again the uniform distribution. This is the PDF. This is the CDF. PDF means again it's a probability density function. What this means is from this, for this random variable, the only possible value is between A and B. Okay, so outside of A and B is 0. So between A and B, this is the flat, constant, which is 1 over B minus A. So it's 1 minus B minus A means the length of this. So this is the probability density function. The CDF basically do the integration of this. It's a straight line like this slope. So this is less than A should be 0. Then between A and B should be straight line, and bigger than A then should be flat, should be 1. So here is the CDF again is the probability. So that's why CDF always something between 0 and 1. But for PDF, this can be anything. But for CDF, it's always between 0 and 1. So less than A, which means there's nothing there, no any probability. So that's why anything smaller than A is 0. And between A and B, you start to do it's a constant. You start to do the integration. If you can remember this thing, you do the integration for a constant, then you get a slope. You get a linear model like this, and then after you reach the B, then you get the probability is 1. After B, that's everything. That's already included everything. So that's why after B is a flat 1. It cannot be bigger than 1. That's the I just mentioned that for the CDF, this is always non-decreasing. It can be a flat, but it have to be increasing flat. It cannot be decreased. So that's the property. The minimum is 0, maximum is 1. So this is the property of the CDF. Okay, so this is the if I write down this again, if I write down this into a mathematics formula, is this. Okay, this fx is a probability density function. It's 1 over b minus a if this x is between a and b. Otherwise, it's 0, which means exactly this. If outside of a and b is 0, then between a and b is 1 over b minus a. So this is just read into a mathematical form. If I write this down as a mathematics form, which is, if x bigger than b is 1, which means this side, and if between a and b this is like a linear model, this is x minus a over b minus a. So a and b, this is the constant numbers, like parameters, okay? And less than a is 0. Which means less than a here is 0. So just try to, this is the figure, but this is just mathematics. So this is how this is the uniform distribution. Now this normal distribution, and for the normal distribution, this is the probability density function, and for this is for different kind of normal distributions, and that for standard normal is this blue line, which means it's centered at 0. Okay, and it's a symmetric. It's normal distribution always symmetric. Around the center of this curve is a kind of bell curve, as you know. And so there are two parameters. One is this center mu. I will talk about these things later, and which is the center of this symmetrical curve. Another one is sigma squared. Sigma actually is the variance. That variance try to describe whether it's narrow or wide, whether it's fat or not. So that's why this blue curve is the variance actually is a 0.2, but when you look at the red one is 1.0. It's much bigger. This variance is much bigger, but also centered at this 0. Okay, so that's the thing, and definitely this mu is the center one. This mu equal to -2, I think here is. And so then this curve basically shifts on this side, centered at -2. So this is what the normal distribution density function looks like. Okay, this is symmetric. But when you look at the CDF of normal distribution, again, for the CDF, and this also non-decreasing, always close to flat, but not that flat actually. and always increasing. This is for, again, for different parameters. This is for 4 different kind of normal distribution CDF. So this corresponding to this 4 density function. Okay. So this is the the graphics. If you write down this into mathematics, okay, for this standard normal for this distribution, basically if you write down the function, actually it's this function. This function 1 over square root 2 pi and exponential negative 1 over 2x squared. So this is just kind of like exponential function, and but this function is exactly that symmetric bell curve. Okay, so this is the function, and this function actually is the function, not the standard normal distribution, but the normal distribution with a center at mu and the variance is as sigma squared. And standard means the mu equals 0, sigma squared equal to 1. That's a standard normal. So this is the mathematical form for the PDF, probability density function for normal distribution. If you ask me what is the mathematical form for this CDF of normal distribution, probably nobody knows what is this. We cannot write down the closed form, but we can still plot this because we can numerically calculate it, but we cannot write down the exact formula for this. But what we are only able to write down this formula, as this, but we cannot write down the CDF. Okay, and here is another distribution, and gamma distribution and exponential distribution. I put these two together because exponential distribution is a special case of gamma distribution. Actually, all these curves you can see, it looks like a bell shape, but not symmetric. But it is skewed, on different ways. Basically, like here, it's skewed on the toward the 0. So this, this kind of distribution, and only a particular special case that is like this decrease. Actually, this is the exponential distribution. Okay, I can show you mathematically the exponential distribution actually is a special case of the gamma distribution. Usually, the gamma distribution is used to describe so-called skewed distribution, because all the normal distribution, I just show you that. So the normal distribution, everything is symmetric. You have to, if you have your data, the data have to be symmetric to something. On both sides of the center have to be symmetric. If your data are skewed toward 0, so this normal distribution is not appropriate. That's why usually in this case, the gamma distribution and even the exponential distribution is a possible choice. As Jackie this morning, or this afternoon, or this morning, I think, when he talked about the differential equations, show you the half-life, whatever that thing is, follow exponential growth. That exponential distribution, growth actually is kind of like exponential distribution. That means the lifetime, how long that a cell can live, is follow an exponential distribution. That's why when you use differential equation, you get I think what you get is the dn dt follow a constant, and these things you can do maybe negative or whatever. So these things, the closed form for this ODE differential equation is the exponential function. Okay, so actually that's why we call this is exponential distribution. So this is the density function or probability density function. The CDF distribution function always always between 0 and 1, always increasing, either flat or increasing. It cannot be decreased. Okay, so it's non-decreasing. Okay, this is the CDF of gamma distribution and exponential distribution. From here, you cannot tell which one is exponential distribution because it's a special case. Actually, I think it's the red one here, and it's this one. This one is exponential. The rest of them are hard to tell. And why is that? Because when you write down the PDF or probability density function for gamma distribution, this is a general form for the gamma distribution. Okay, what this means? Lambda is a parameter, and also this R is also a parameter, and this is the x to R minus 1's power. This is e to negative lambda x. So x must be a positive number. This right now we are talking about x is a positive number. It's not like a normal distribution can be negative, can be positive, but this gamma distribution is x has to be positive. And this gamma actually is a so-called, is a gamma function. By definition, is this. There are some gamma function properties. You can look at some mathematical book. And I'm not sure you're supposed to learn this in high school or college. But so this is the basically gamma function. If you know the R, then you should be able to calculate this gamma function based on the formula, this or just all the integration. And for exponential distribution, if this R here equal to 1, this gamma distribution reduced to the exponential distribution. Because exponential distribution is like, the formula is like this, just lambda e to negative lambda x. So lambda is a parameter, okay? And because when R equal to 1, you can see R equal to 1, this is 0. This guy's zero's power actually is 1. So this term is gone. And also, if R equal to 1, gamma 1 actually also equal to 1. Okay? So this term, these two terms is gone. That's why only we left this lambda times this term. So that's why exponential distribution actually is a special case of gamma distribution when this parameter R equal to 1. Okay? So that's why when you plot this, you cannot tell, this here is the exponential distribution CDF, but this is all the other gamma distribution. Okay? But when you plot this PDF, then the exponential distribution, the shape is different from the rest of the gamma. So depends on your data. That's why when you look at your data, you want to see what distribution can describe your data distribution. Okay. First, if your data is symmetric around something, you can use normal. If that doesn't work, you can pick the gamma distribution is more flexible to deal with this skewed, non-symmetric distribution. And the exponential basically even deal with this kind of shape of this distribution. So that's quite flexible. So that's the usually actually the people use this gamma distribution or exponential distribution to describe something's lifetime. Like for example, a cell's lifetime, how long a cell will live. That time to some event. Usually people use this gamma distribution or exponential distribution to describe, because this distribution also try to describe something must be a positive number. Something's lifetime is a positive number. Somebody like, for example, how long a person can survive or can live. That's also the positive number. Nobody live for negative, but so that's why usually gamma distribution and the exponential distribution is very popular. Try to describe something's lifetime. In particular, I think in reliability research try to study how long a product can survive. Like for computer, how long the computer can survive. You use it. So that's usually follow either a gamma distribution or exponential distribution. Okay, that's the very popular thing. Okay, and that's all the, I just give you a very brief introduction about a random variable and their distributions. In particular, there's two things. For discrete random variable, there's a so-called probability mass function, and for continuous random variable, there's a called probability density function, PDF or PMF. And both of them have something in common, which is the cumulative distribution function, or just simply called distribution function. Okay, that's just some of the basic concept about the random variable. So then we can use the random variable to describe your data. And when you get the data, actually, I turned the gear to talk about more things related to the data. When you get the data, you always use the several concepts. One we call, so-called summary statistics. When I talk about summary statistics, first thing you want to describe the central tendency of your data, which means you've got a bunch of numbers. You want to use usually that you use the mean, which means the average, or median to describe the center of your data. This is the thing. And sometimes probably use a mode, and probably I'm not sure what trimmed mean is. And a geometric mean, there's different kind of mean, basically try to describe the center of your data. And here is the plot for this. I think, let me see, the mode, for example, mode means the maximum number. If this is the PDF, okay, this figure is a probability density function, and the maximum, point or the peak of the PDF is called a mode. And the median actually means if the line is here, means the distribution, okay, on both sides equal to 50-50. What that means is the area under the curve is 50%. They are equal. That's called median. Why is that? When we talk about, when we talk about this distribution function, basically the area under the curve of the distribution function, or do the integration, should equal to 1, because that's the area. The whole area on the curve of a distribution is actually the CDF equal to infinity, up to infinity. That's the the probability of let me see. That's the probability of x equal to infinity, which means if you do the integration for the whole area, this probability should equal to 1. It's the maximum number of that CDF. So the area under the curve of any probability density function should be 1. So that's why when we do this median, which means that on this side of area on the curve or this side of area of curve equal to 0.5 and 0.5. That's the equal. It's the line to cut the area on the curve by 50-50. Okay, and so this is the mode, median, and mean actually is the expectation. Which, if you have symmetric, usually is same as the mode. If it's not symmetric, like the blue line here, I think it's blue, is the mean. Mean actually is the is the weighted. Okay, I have to say, the mean actually is the weighted average of random variable, weighted by the probability density function. I will talk about these things later about this concept. So basically, you use this kind of mean median mode to indicate the central tendency of the data. The trimmed mean, okay, probably heard, I'm not sure you heard about this. Trimmed mean is sometimes your data have some outliers. You don't want to one or two outliers dominate the mean or dominate the center of your data, because one number, if it's outlier, and then you take the average, everything is dominated by that particular number. What usually people do is, it's like when people try to rank something, and also we are going to have a poster award for our symposium. What I'm going to do is I will ask, for example, I'll ask 10 people to give scores for each of the poster. And what I will do is I will drop two highest numbers and two lowest numbers, because some people may be biased or others. Then I take the average of the 6 numbers in between. I drop the two highest, two lowest. That's called trimmed mean, because I trimmed two lowest, two highest. Okay, so this kind of mean is more robust. It's robust against outliers. So this is this is the kind of like a robust center of the data. Okay, so this is called trimmed mean. Geometric mean, basically you take the log, then you take the average or mean average. So that's the geometric mean. So people use different kind of measure to measure the center of the data. So that's the central tendency. Another thing is for summary statistics is to try to measure the spread. Okay, so this, you probably also know this. Usually you can use a range of your data. So tell people the range, and then people roughly know the spread. And also, most popular thing is you use is a standard deviation or variance. So this is what you know. I will talk about this definition rigorously later. And also use the interquartile range, means like 75 percentile up to, or 25 percentile to 75 percentile, or whatever, or 10 percentile versus 90 percentile. What's that range? It's instead of the whole range, but you can give the quartile range. So that's another way to describe the spread of your data. So this is different way. And also, another summary statistic is so-called skewness. Sometimes you use the center and also tell people spread. This means that your data is symmetric. Otherwise, these things is not a good description about your data if your data are not symmetric around your center, right? So sometimes we try to describe the skewness. So this seems like you skewed to the right. This this is skewed to the left. I don't know, this right way. Which one? That depends on which one, left and right. Whatever skewed on this way. It should be left, right? This is right. And I'm not sure it's opposite. And so this just this show that the data is not symmetric. So you have to, if a good description about data is tell people the whole distribution. But sometimes this whole distribution is difficult. You have to graphic. You have to use a plot to show it. If you want to use a number, this is hard to do. So that's why sometimes we use the numbers if it's symmetric. If it's not symmetric, we can do some plot like this to tell people your data is skewed or not. Another visualization way is this like so-called box plot. And for this box plot, let's look at the right-hand side is a standard box plot if there's no outliers. So this box plot basically is tell you that this line is the median, and this line is a geometric mean, and this green line is standard mean. So basically this box tell you the mean, and this is I think is tell you 95 percentile or 90 percentile. But it's different box plot can do different things. And also if you have outliers, this box plot also can tell you there's some outliers here. Okay, so this is this is a good this basically is a summary. This visualization tell you both the central tendency, where is the center of your data in different ways. At the same time, tell you the spread out. You can you can do this actually. Usually people do this either by one standard deviation or two standard deviation or whatever. You can do like a quartile, like 25 percentile to 75 percentile. That's okay. So you can do different ways of this kind of box plot. But this is a good visualization about that summary statistics of your data. Okay, and also is for this is good to show that here is the outlier, like two outliers here. Most of the data are here, but these 2 points, tell you this outlier. If you use the standard mean or average to do this, these 2 time points can dominate the mean. Okay, that's why sometimes you need to use the trimmed mean in this case to indicate the center of your data. Okay, this is the summary statistics thing, and there's more summary statistics. And here I just introduced a concept so-called moments. So when you get data, that means data means you get x1, x2 up to n numbers. Whatever the number experimental data numbers are, you have n. You use n to indicate your sample size, right? You get n numbers. And sample moments means you just take this so-called case sample moment about 0. What that means is for each of these number you take case power. So if you think it's second sample moment, means you take the square for each of these numbers, then average them, or sum them together divided by n. Basically, you average them. This is called the second sample moment. If you take any case power for each of these number, then you just do the average. That's called case sample moment. Okay. So and if k equal to 1, which means the first sample moment, what that means? 1 means you just take the 1 power means you do nothing. You just take the simple average of all your data. So this is a simple average of all your data. So this is called sample mean. Basically, this is called sample mean. Usually we just use a notation like x bar subscript n, which means this is all the x. I have n numbers. I take the average of these n numbers. So that's why I use bar means this is the average. Okay. So this is just some of the statistical notation. And also there's another concept so-called case sample moment about x about this sample mean. This is sample mean here. So what that means is instead of directly take the case power here, you subtract this sample mean first. Each of these number subtract this sample mean first, then take case power, then do average. So in this way, we call case sample moment about this sample mean. So here we usually will call this case sample moment about 0 because we didn't take anything out. So this is just a basic concept. I need this concept when I try to estimate parameters for distributions. Okay, so this is the sample thing. Then we talk about some basic statistical inference. Okay, when we talk about the basic statistical inference, when you do experiment, there are different kind of data you may collect. Data may be continuous, as I talk about continuous random variable. Maybe discrete, just binary. You just maybe do HIV test. You get a bunch of people positive, negative, just 0, 1 numbers. Maybe categorical data, and you may get different kind of data. And or sometimes probably you do longitudinal studies. The longitudinal study, you measure something for a person repeatedly several times. Like when we try to do AIDS clinical trials, we usually measure patients' viral load for every 3 months. Maybe for you follow for 3 years, and then that means for each subject or each patient you get multiple measurements for the same thing, for the viral load. So those kind of data is called longitudinal data. Sometimes you may get data like so-called time to event data or survival data. If you look at, if you do the cancer studies, there are many studies try to compare the survival time of cancer patients. What you measure is how long that cancer patient can survive if you give treatment or without treatment, or compare 2 different treatments. So you can, you may get different kind of data when you do statistical inference. And also, when you talk about inference, there are 2 big types of inference. Usually have these 2 big types. One is so-called estimation. Another one is called hypothesis testing. And for estimation, we have 2 things also. One is the point estimation. Another one is called interval estimation. Basically, give you a confidence interval. And for the test, basically there are different kind of hypothesis testing. Like you compare 2 things or compare 2 different things, whatever. We will talk about this, testing on Tuesday. And but today I don't have time to go over all these things because we are going to do this, on Tuesday. Today I will give you just a very basic concept about this point estimation for a very simple continuous and discrete data. Okay, so then it just give you some feeling about what's the principle to do statistical estimation. Okay, so that's what I'm going to do, then I will be done. Okay, and by definition, the point estimation, what that means, point estimation means when you collect a bunch of data, and we call this data set as a random sample from a distribution, follow a PDF, from a distribution with a PDF or probability density function fx data. Okay, again, if you know the probability density function, you should know the CDF also. That means you should know the distribution function. Okay, this PDF and the CDF, they are one-to-one correspondence. And the only thing I don't know is the theta, is the parameter theta. For example, I just mentioned that when you try to calculate the probability of HIV person, when you try to calculate the probability for a person, you randomly select from in Rochester whether that person is negative or positive. In order to know that probability, you need to do experiment to estimate that probability. So that probability will be an unknown parameter that need to be estimated based on the data. Okay, so the point estimation for this parameter theta is we use the value of so-called statistic, which is the function of all your data. You collect the data, and to estimate, you just need one value based on all the. You need to summarize your data into one value to estimate this parameter theta. That's so-called point estimate. You just need one value for one parameter. Okay, and definitely if you have the estimate of this theta, you can estimate any function of theta. Okay, theta square, whatever, theta cubic, or log theta. You can do any function estimate. If you know theta, you also know the function of theta. So that's another concept. So this is the point estimation. And interval estimation. So interval estimation means you need to give 2 values based on your data, so that the parameter will fall in that 2 values, or fall in that interval with some probability. For example, here, so if your data follow a normal distribution, like symmetric bell curve, and the parameter falling within the interval plus minus standard deviation is 8.3%. That's the probability. If you fall within 2 standard deviation, you know, plus minus 2 standard deviation, this probability is about 95%. Okay, and if you fall within plus minus 3 standard deviation, that's almost 99.7%. So if you give what is that interval is, and then also you give that probability, what probability that your true parameter will fall in that interval. That's the so-called interval estimation. You not give one value, but now you need to give 2 values based on your data. Just give you intervals. Okay, so that's the interval estimation. And basically, when we talk about parameter estimation for distribution, there are 3 basic methods or principles, I call. Okay, one is called moments. Another one called maximum likelihood estimators, and the third one is the Bayes estimators. There are some others, but these 3 things, or these 3 principles are mostly important, very popular. Probably 90% of estimate, point estimation based on these 3 principles. Okay, and so before I introduce what I will talk about, before I will briefly talk about these principles, I will introduce more properties of a random variable. And one property, is the so-called, expectation or mean of a random variable. Or I forgot to tell you that I usually use RV to indicate the random variable. Okay, not the real RV or whatever recursion vehicle. Not that. So this is the, when I talk about expectation or mean of a random variable, what that means. So expectation of x for discrete random variable means the x multiplied by the probability mass function, then do the summation. What that means, this is like the weighted average, the weight by this probability mass function. For continuous x, which means this x multiplied by the PDF, then do the integration from negative infinity to positive infinity. Again, this is like a weighted average for this x, weighted by this probability density function. Okay, so this is the weighted average. Basically, it means the expectation or mean of this random variable. Okay, and the variance of random variable. So you probably know this. The variance of random variable is the expectation of the x minus mu. Mu is the expectation. Okay, it's this. Okay, the expectation of it. X minus mu the square. Then do this expectation again. This expectation again. This thing multiplied by PDF, then do integration. Or if it's discrete, you have to do the weighted average of this thing. Is the expectation. So expectation always the weighted of something, weighted by this PDF or by probability mass function. Okay, that's the expectation, and so that's the variance. And the expectation of any function of x for any function, expectation of any function is again this function weighted by PDF. If this is continuous, if it's discrete, then you need to replace this integration by summation. So basically, the expectation means is the weighted average of something. Okay, so that's the concept of this. So what this means for any, if I know this PDF or this PMF, then I can just do the integration. I can get I can get the expectation of this for or any of these functions. I can get this. But the question is whether I know the PDF exactly. Exactly means do we know all the parameters in the PDF? Okay, that's the question. Okay, so and another thing is so-called population moments. I just talked about sample moments. The sample moments is based on the data. Okay, when I talk about the sample moments here, you have to have the data that you do this kind of the case sample means case power, then do the average. So you know the numbers, then you can calculate the sample moment. When I talk about the population, I don't have much time. When I talk about population moments, means similarly, when I talk about case moments, again, this is like case power of this x, then take the average. This is the take the average, weighted average based on the PDF. Okay. Now I focus on the continuous random variable here, and for the discrete random variable, you just replace this by summation. So that's all. So again, when you talk about case moment, you do the case power of this x, then weighted by this PDF, and do the integration. So this is the so-called case moment of this random variable x. So basically, it's the expectation of x to case power. Okay, and when you do this integration, then if you know these parameters of this PDF, then you can get it. If you don't know these parameters, basically this is the function of these unknown parameters. That's why usually I write down into this mu k as the prime as the function of these k parameters. Okay, and another concept is so-called central moment. Central moment again is this case power. Before I do this case power, I subtract this mean. This is the expectation, mean. Okay, this is the mu. Mu is the expectation of x. So this is so-called case central moment. Okay, and again, this is the sample moments is corresponding to this, very similar to this, but this is just the kind of like a theoretical population moments. And when you have your data, you have the case sample moment based on your data. So then when I talk about moments methods for parameter estimation, what I use the principle is I just let these sample moments equal to population moments. Okay, again, because your sample moments is just based on your data. If you have your data, you can calculate this. Your population moments is a function of your parameters. So if you let these two things are equal, then what you get is this parameter function equal to your data, your numbers. If you know the average, for example, this is the first moment, then this is just the number. Okay, if you know this number, then you get one equation. You get a bunch of these equations, for your parameters, and then you can solve this algebra equation to get the estimate of the parameters data. So that's the idea how to make your theoretical moment equal to your sample moments related to your data. Then you can derive your population parameters. That's the idea. And I can give you some of the example. So this is for normal distribution. For normal distribution, we know the PDF of a normal. If you get the n numbers from a normal distribution, x1, x2, xn, we know the PDF function, as I mentioned earlier. I can write down the PDF of normal distribution into this. Then based on this, I can derive the first population moment from this is equal to mu, equal to this parameter. This is the first population moment. The first sample moment basically is just the first sample moment is just the average of your data. Okay, it's just sample mean. So if you make these two equal, then you get the mu equal to x bar, which means this is the average of your data. So then it's the moment estimation for your parameter mu is very simple. Take all your data, take the average, then that's the estimate of this mu, based on this so-called moment methods principle. Okay, so that's very simple. How about the variance? How to estimate this parameter variance? This parameter, then you need to get the second population moment. If you derive the second population moment, this is the sigma square plus mu square. Okay, then the second sample moment, basically you take each number of your data as to the square, then take the average. Then you make these two equal. When you make these two equal, then sigma square will equal to this guy minus mu square. You already get the mu from here, right? Mu is the average of your number. So then you know this mu square, that is the average, square. Then this is the second sample moment. If you know your number, you take the square for each number, then take average. Then this you take the average first, then square. Then take the difference of this. That's your variance. So that's how you use the moment principle to estimate your parameters. So I don't have time to talk about a discrete distribution. Here is I use a Possum distribution actually, to do this. If you have a Possum distribution, and the first moment is the lambda, which is an unknown parameter, and the first sample moment is just again is the average. Then it's very simple for Possum distribution. This parameter lambda again equal to the average of your data. So this from the moment principle, the estimation is very, very simple actually. And for the maximum likelihood, and Let me use another 3 or 5 minutes to finish. And for the maximum likelihood, what that means is when you have a random sample x1, x2, xn, we assume this follow a density function f. Then what the joint distribution of this all your numbers, you get n numbers. So each of these, each of these sample actually follow a PDF. If you plug in, this each of these number into PDF, you get a bunch of this. Then you multiply them together. This is so-called joint distribution of your data, and actually also called likelihood function. So what that means, this likelihood function means this is the probability you observe these n numbers. That's the total probability. Then you try to maximize this to get the parameter theta. So what parameter theta can make you most likely to observe the number you have at your hand. So this is the principle and to do. And I don't have time to talk about how to do this, but once you write down this the function, then you can just try to get the maximum number of that function to get the maximum likelihood estimate. Like Jackie just mentioned this afternoon about how to optimize the function. So you need to use that technique to get this maximum likelihood function. So I will skip some of this the maximum likelihood function. And another principle is the so-called Bayes estimator. Probably you heard about this. Basically, Bayes parameter is a different philosophy. This assumes the parameter theta actually is a random variable. Not only data are random, but the parameter also random, and follow a prior distribution. That basically, Bayesian people think the parameter is random, and they have some prior. Then if you get additional data, they try to use the data to update your prior. So this is the basic concept of this Bayesian method. And Bayesian method actually is good to combine the data and some prior information. It's an information combination method. It's not it's not really only use your data, but use the data and some other information to do it. So this is the thing. I would skip all these properties and briefly just overview what we will do in day 3, on Tuesday, and we have a whole day again for statistical lectures. Today I just give you a very brief introduction about random variables, distributions, maybe some very brief concept about estimation. Then on Tuesday, first I will talk about experimental design. This will relate to the whole process, how you design your experiments, and then we'll talk about more statistical inference. Then also Hua Liang will introduce the R, which is the software, statistical software, how to use this R to do some basic statistics, and also some little bit advanced methods. And then Hongmei will talk about some examples from immunology studies, to do statistics. Then we will have 1 hour talk about statistical methods for bioinformatics data, probably for microarray data. And then finally on the last lecture, Jackie will come back to talk about statistical methods for computational models. And that will finish the whole day of statistics. That's on Tuesday. I think that's all I have. Okay. Sorry,